Hello everyone, welcome back to another class of fundamentals of particle and fluid solid processing. Until the last class, we have seen the fluidization, the fundamentals of fluidization, and during that we have also find an analogy of fluidization with the opposite of settling. Now, this settling has immense importance in this particular area, because when we try to separate solids from fluids, there are several techniques available, and one of the primitive as well as less expensive technique is the settling or sedimentation. So, here what happens that in a pool of liquid or some fluid, we put those solid particles mixture, and we have seen the fundamentals that due to different size, density and all these, the particles will have its different terminal velocity while coming downward to that top surface. Now, based on that settling speed, settling time, you can segregate different size particles. In fact, we solved a problem during the particles motion in a fluid on that section. We also in the fluidization we introduced the concept of hindered settling, because when there are multiple particles, the simple scenario that we have understood for single particle movement in a pool of liquid, in case of collection of particles, that physics is not relevant. So, these couple of initial slides I have again kept it for the sake of coherency, so that we can quickly go through this concept or the fundamentals once again before we start to look at these different settling phenomena. So, the settling operations we can operate in a two different way. That one is the batch settling, that we just put certain particles in the fluid and we wait for that to sediment, the settling to have its final stage. And the other case, there is a continuous operation which is called the continuous settling. So, we will see these two in details in this section. Now, before that, as I said, just look, we will again glance through these equations, expressions, so that we can find we can remember the relevant terms. Is that when there are collection of particles, this viscosity, density of the mixture has been defined in terms of effective viscosity as well as the average density. How we have done that? It is that viscosity becomes a function of the void fraction or the void fraction occupied by the fluid phase, and the average density is basically this volume fraction of the liquid phase multiplied by the respective fluid density, and the addition of the solids fraction multiplied by the solid density. Now, we know that in Stokes regime, this is the drag coefficient, which now under terminal velocity condition we can write this simple balance that we have already seen, and we find a relation between this terminal velocity based on the relative velocity concept, okay, and a single particle terminal velocity. By comparing these two expressions, we find this relation that the hindered settling velocity is basically the single particle terminal velocity multiplied by the void fraction multiplied by a function dependent on the void fraction or the volume fraction of the fluid. Now, this expression we have also seen that how it depends or what are its expression in different regions, okay, because if we assume that the fluid and particles are incompressible and there is constant volume flow rates of fluid and the particle. So, we can write this, we can find out what are the superficial velocity for the solids and the particle, okay. And then the flow area occupied by the fluid is basically is fraction multiplied by the total available area. Similarly, the area occupied by the solids is its solids fraction multiplied by the total available area. We do this conservation, okay, because the mass is conserved, and then we find that this actual velocity, okay, is this superficial velocity divided by the respective volume fraction. So, superficial velocity of each phase, be it a fluid phase or the particles, it is their corresponding superficial velocity divided by respective volume fraction. These things we have already seen, but just to recall, I am showing you these expressions once again. Now, in case of batch settling, that means say you have a measuring cylinder, okay, and then there is a pool of liquid is there, some solid particles are now settling, okay. This is at, let us say, certain time t, these particles will sediment or will settle at the bottom of this measuring cylinder at a certain time. Now, in batch settling, there is no inflow or outflow of this particle or say the fluid. So, for the whole system, Qp plus Qf, that is the flow rate of particle plus flow rate of fluid, is basically 0. This is a batch system, which we can write because it has a uniform cross sectional area. So, we write that in terms of its actual velocity. From this expression, we can have this one, that what is the UF, which is minus UP multiplied by 1 minus epsilon divided by epsilon. Now, this UP minus UF is basically the relative velocity, okay. Now, here this relative terminal velocity, we have also seen its expression in the previous slide, that this is nothing but the single particle terminal velocity multiplied by this factor, okay. So, this expression can be written in this form, that now we have this one, which if we now replace it here, we get that what is UP in terms of UT, actual velocity of the particle in terms of the single particle terminal velocity, what is the relation. So, from here what we get? We get what is UF. We replace this here and we get this final form of UP, which is the actual particle velocity in case of batch settling, okay. So, that means this dimensionless velocity, or now the point is that we have seen, before I go into that, the point I have seen is that this function, what its expression, because then you can calculate what is UP. Now, this expression theoretically has been shown that for uniform spheres and solids volume fraction or suspension of less than 0.1, this Fe, the function of epsilon, is basically epsilon to the power 2.5. Okay. We have also seen these two criteria, that when the particle Reynolds number is less than 0.3, the epsilon is basically 2.65, and when it is in Newton's law region, this epsilon is basically 0.4. So, in Stokes law region, epsilon, the function, the viscosity will be influenced by epsilon to the power 2.5, 2.65, okay. And in case of Newton's law region, when this drag force is independent of the viscosity, there we have epsilon to the power 0.4. In general, UP, that means it's basically UT multiplied by epsilon to the power n, because if you replace this expression in here, you basically get these UP relations. So, UP is basically UT multiplied by epsilon to the power n. We have also seen, or also have covered, this expression by Khan and Richardson, that covers the entire range of entire range of Reynolds number, and predicts the value of n, where x and d are the particle and the vessel diameter, or the measuring cylinder diameter in this case. And Archimedes number, we already know this expression. And in this case, again, x is logically the mean surface volume diameter in case of irregular or non-spherical particles. So, this we have seen. Now, the point is that this, if now we know that what is the actual particle velocity, based on the Reynolds number region, you can find out what is the Richardson-Jackie expression. This is the famous Richardson-Jackie expression, okay. And then you can find out what is UP, that is the actual particle velocity. In terms of volumetric solid settling or solid settling flask, we can write UPS is the actual velocity multiplied by its volume fraction, which again we write in terms of the terminal velocity. We replace the expression of UP by UT multiplied by epsilon to the power n. So, which means we have got the volumetric solids settling flask in terms of the single particle terminal velocity and the volume fraction of the solids and the liquids. In terms of a dimensionless quantity, if we divide this by UT, we get this expression. Now, if we plot this, that means the plot of this parameter on the left hand side and 1 minus epsilon, which is the solids fraction, we find there is a maxima, because a simple thing of making doing the derivatives, first and second derivatives, will give you these ideas, that this curve or this plot will have a maxima at epsilon is equals to n by n plus 1 and inflection point at n minus 1 by n plus 1. So, this plot would look like something like this. that is shown here, this graph, where x axis is the volumetric suspension concentration, that is 1 minus epsilon, and y axis is this non-dimensional quantity, non-dimensional settling velocities. So, it will have a maximum at n by n plus 1, and this inflection point is at n minus 1 by n plus 1. In case of Stokes law region, we know what is that factor, that n, what is n. Okay. In case of Stokes law region, n is 4.65. So, for Stokes law region, this value, remember this is 1 minus epsilon, becomes 1.77, and here we get at 0.353 something. Okay. Now, the point is that you can think of the scenario like here, that you have this measuring cylinder where you have put it is filled with liquid or say water, and then from the top you have put some sand or that kind of fine particle. Okay. So, there will be in batch settling, there will be a clear interface or discontinuity or concentration. That means, there will be some portions at a certain time where the densities of the particle, the concentrations, basically the concentrations will be higher, okay, and at some portion that would be lower. So, this region you can clearly identify if the measuring vessel is transparent. Now, this interface between the suspension of say concentration C1 will have say a particle terminal velocity of up1, and the region where the concentration is C2, assume that there the particles are settling with a superficial with the settling velocity of P2, the actual particle velocity. Okay. And the interface, this kind of interface, because here let us say the dilute suspension, this is kind of a dense suspension. So, you can identify its interface. Now, this interface say is falling at a velocity u int. Now, these all velocities are basically measured with respect to the vessel walls. Then what happens, that you get this up1 minus u interface multiplied by the concentration in that region, or from interface to inside that region wherever the particles are having the settling velocity of up1 multiplied by its concentration is equals to this downward settling flux multiplied by their concentration in the denser region. If we assume the concept of incompressibility, both particles and the liquids or the fluids, then we can find the rate or the velocity of this interface, which we can write in terms of up1 multiplied by C1 minus up2 multiplied by C2 divided by the concentration difference between these two layers. okay, but these terms, okay, are already, these are the downward velocity flask, okay, or the volumetric flask, particle volumetric flask, because you remember this expression here when we introduce that term, actual velocity multiplied by its concentration. Here the point is 1 minus epsilon is the solid's volume fraction. So, now in settling sedimentation, this volume fractions we typically say its concentration here, or C. So, 1 minus epsilon is basically say the concentration of the suspension. Okay. So, 1 minus epsilon is the concentration of the solids here. So, that is what is designated by C. So, this UPC terms are nothing but the volumetric flasks, this one and this one, which is UPS1 and UPS2. These are the particle volumetric flasks in suspension of concentration C1 and C2 respectively, which means this interface velocity is del UPS divided by the del concentration. In the limit of C tends to 0 or the concentration tends to 0, that means the clear liquid or the clear fluid, this we can write in its derivative term, that dups divided by dc. That means the plot of this UPS and the concentration, okay, its gradient at concentration C will give you the velocity for that layer of suspension containing the concentration C, isn't it? Because here you get this expression, this is the interface velocity, okay, and this is the derivative of this UPS with respect to C, the concentration. So, UPS versus C, okay, at any point the slope of the graph of this curve will give you the velocity of the layer corresponding to that concentration, and interestingly the connection or the chord that will join two concentrations, okay, that slope of that line will give you the velocity of the interface, which means here for example C1, if it is 0, that means it is the clear suspension, that is the clear liquid, there is no suspension. Concentration of the solids are 0, that means the pure fluid, okay. As you increase the concentration here, fine. So, say at C3 all particles has settled or the sedimentation is complete, okay. So, it is a settled bed, it will have solid particles filled here and there is a clear liquid at the top. So, in this case the connection between C1 and say C2 for one concentration, the slope of this chord that connects C1 and C2 in this graph will give you the velocity of the interface having the concentration C1 and C2. So, if this is the concentration C1 and this is concentration C2, this slope of this line will give you the velocity of this interface. Similarly, this C2, C3, the slope of this line will give you the velocity of the interface between concentration C2 and C3. Okay. So, if you can come up with this suspension concentration plot with the volumetric flask, then this rate of falling of this interface will be easier to calculate, as well as you can calculate the velocity of the layer that has a certain concentration, that at what would be that value. Now, in a batch settling test, if you do that yourself or in a laboratory, that initially say you have a suspension of concentration Cb, and the interface height or the height of this whole suspension is h from the bottom of the vessel. Say somehow you have mixed it properly, the concentration of the solids in that vessel or the cylindrical tube is, they say, uniform. You have made it somehow by vigorous mixing, by shaking, and then you just keep it having it upward so that the particles can settle down at the bottom of the tank or vessel or that measuring cylinder. And if you can monitor the position of the interfaces, okay, in time, you would see that there would be two types of settling phenomena. In one type, what will happen, that this kind of clear liquid zone, that is zone A, would be there. There will be a clear sedimented portion, that means the particles that have settled there, okay, and there will be some intermediate portion, that is of the concentration Cb that you initially started with. As you leave it with time, ultimately there will be a clear liquid zone or the clear fluid zone and the sedimented zone, where the concentration of this sedimentation is Cs and the concentration of particles in the A zone is 0. Now, if you draw, because you have monitored this interface height in time or the position of interfaces with time, if you plot that, the plot would look like that is presented here. That is, if this is the height of interface and this is the time, this is the height of interface h and this is time, then AB basically stands for this interface height, the way it is decreasing, and this is the interface between B and S, the way it would increase, and eventually it would come to a position where we find the clear interface of the sedimented part and the clear part, which is AS. It would march at a certain point of time and after that it would be as it is, because that is the time when the clear sedimentation has happened or complete sedimentation has been taken place. The other type is that, say, there will be the formation of a zone of varying concentration with position, which means this zone will be introduced or formed in the other type, that you have a clear section, the section with the initial concentration that you started with, a clear sedimented section, in between there will be a portion of solids where the concentration will vary between the two extreme, that is the concentration Cas and the concentration Cb, and this will vary in position. It will have a range of concentration in that range, unlike in the previous case where this was of uniform cross section, the whole section. After a certain time, again this section B or the zone B would vanish, and again it will be a section E where this concentration will vary with position. And at the end of the test, like the previous one, there will be a section A, a zone A and zone B where we started with that solution or that suspension. So, these two types of settling are typically observed, and this phenomena actually depends on the initial concentration that you started with or the Cb. And in this case, if you start with this height of this graph or this interfaces, you would see the similar kind of the pattern, but there is this BE mean, that means the interface between the B this position and the maximum that could have been just at the end of this E section and at the beginning of S. Okay. So, this would typically happen if this rise is much faster, that means this interface height rises much faster than the decreasing height of AB. So, how it happens? Again, it depends on the initial concentration that you start with. Either you can land up in type 2 settling, if we say this is the type 2, or the previous one. We will see this in details. We will continue on these ideas in the next class, and till then, thank you for your attention.